The invisible painters. Light meets matter. Close your eyes for a moment. Right now, in this very instant, something extraordinary is happening all around you. Light is touching matter. Photons, those invisible messengers of energy, are colliding with the atoms and molecules that make up everything you see. Some of that light bounces back toward your eyes. Some is absorbed, converted into heat or stored as chemical energy. And in that delicate dance between light and matter, color is born. Not as paint on a canvas, not as pigment in a bottle, but as pure physics expressing itself through the language of chemistry. Have you ever wondered why a rose appears red while a leaf appears green? Why the ocean stretches before you in shades of blue, and why the sunset paints the sky in oranges and purples that seem almost impossible to describe? The answer lies not in the objects themselves, but in an invisible conversation between light and the atoms that compose those objects. This is the story we are about to explore together, a gentle journey into the hidden chemistry that paints our world. Before we begin, I would like to invite you to subscribe to the Relaxing Science channel. Give this video a like, and if you feel moved to do so, share in the comments where you are listening from right now and what time it is there. This helps us understand our global community and creates a space for connection across distances. The truth is that color is not actually a property of objects themselves. It is an experience created by the interaction of three fundamental elements: light, matter, and your own perception. When you look at a colored object, you are witnessing the result of billions of atoms and molecules responding to electromagnetic radiation in ways that have been written into their very structure by the laws of physics. The chemistry of color is, in essence, the story of how light and matter communicate. Imagine standing in a forest at dawn. The first rays of sunlight filter through the canopy above. Those rays contain every color of the visible spectrum: reds, oranges, yellows, greens, blues, indigos, and violets, all traveling together in waves of different lengths. When that sunlight touches a leaf, something remarkable happens. The leaf does not appear green because it is made of a green substance. Rather, the leaf absorbs certain wavelengths of light, particularly the reds and blues that would be useful for photosynthesis, and reflects the green wavelengths back toward your eye. The green you see is the light that the leaf did not want, the light it rejected and sent back into the world. This principle underlies all color in nature. Objects appear to be certain colors not because they possess those colors inherently, but because of what they do with the light that strikes them. Understanding this distinction is the key to understanding the chemistry of color. It is about what happens when light meets atoms, when energy meets matter, and when the quantum world reveals itself through the colors we see every day. In the coming moments, we will explore the mechanisms behind this magical interaction. We will descend into the atomic realm where electrons dance in shells around nuclei, absorbing and releasing energy in the form of light. We will see how the structure of molecules determines which colors they absorb and which they reflect. We will travel through autumn forests, dive into crystalline depths, soar with butterflies on iridescent wings, and gaze at distant planets painted in colors that tell us about their composition and history. The chemistry of color connects the microscopic and the cosmic. It explains why iron rusts into reds and oranges, why copper turns green with age, why the deepest oceans appear blue even though water itself is colorless, and why fireflies can create light without heat. Every color you have ever seen has a chemical explanation, a story written in the language of electrons and photons. As we move through this exploration, you will notice that science and poetry are not opposites. They are partners in understanding beauty. The more we understand about the chemistry behind a sunset, the more magnificent that sunset becomes. The more we know about the molecular structures that create the colors of a butterfly's wing, the more we appreciate the elegance of nature's design. This is a journey meant to calm your mind while expanding your understanding. You may find yourself drifting into a state of peaceful contemplation as we explore these concepts together. That is precisely the intention. Science, when presented gently and poetically, can be a doorway to relaxation and wonder. Let the information flow over you like water. Do not strain to understand every detail perfectly. Simply allow yourself to be carried along by the current of discovery. The chemistry of color is fundamentally about transformation. It is about how invisible energy becomes visible experience. It is about how the quantum mechanical behavior of electrons, following rules written into the fabric of reality itself, creates the rich tapestry of colors that make life beautiful. From the deepest ocean trenches to the highest mountains, from the smallest flower to the largest planet, color tells the story of matter responding to light. As we begin this exploration, settle into a comfortable position. Perhaps you are lying down, ready to drift towards sleep. Perhaps you are sitting quietly, seeking a moment of peace in your day. Whatever your situation, allow yourself to become fully present. Notice your breathing. Feel the weight of your body supported by whatever surface holds you. And now, let us move forward together into the invisible world where atoms become painters and light becomes the medium through which they create all the colors you have ever known. The Dance of Electrons. Understanding atomic structure. To understand color at its deepest level, we must first understand the architecture of the atom itself. Everything in the universe is made of atoms, and atoms are far from the simple, solid spheres that early scientists imagined. Instead, they are dynamic systems of energy and movement, with a nucleus at the center and electrons orbiting in regions of space called shells or energy levels. It is within this atomic structure that the chemistry of color begins. Imagine an atom as a miniature solar system, though the comparison is not perfect. At the very center sits the nucleus, a dense collection of protons and neutrons held together by forces far stronger than gravity. Surrounding this nucleus are electrons, negatively charged particles that exist in a state of perpetual motion. Unlike planets orbiting the sun in fixed paths, electrons do not follow simple circular orbits. Instead, they occupy regions of probability called orbitals, where they are most likely to be found at any given moment. These electrons are arranged in shells around the nucleus, and this arrangement is crucial to understanding color. The shell closest to the nucleus is the lowest energy level, the most stable position. Electrons naturally want to occupy the lowest available energy level because it is the most stable state. However, there are only a limited number of positions available in each shell. The first shell can hold up to 2 electrons. The second shell can hold up to 8. The third shell can hold up to 18, and so on, following mathematical patterns that emerge from the quantum mechanical nature of reality. When an electron absorbs energy, something remarkable happens. That energy can knock the electron up to a higher energy level, like lifting a ball from the ground to a shelf on a wall. The electron moves from a lower shell to a higher shell, occupying one of the available positions at that higher energy level. This state is unstable. The electron does not want to stay there. It is like a ball balanced precariously on a shelf. It wants to fall back down to the ground. When it does fall back, it releases that energy in the form of light, a photon that carries away exactly the amount of energy that was absorbed. This process, the absorption and release of light by electrons, is the fundamental mechanism of color. Different elements have different arrangements of electrons, different numbers of shells, and different configurations of orbitals. This means that different elements require different amounts of energy to move electrons between shells. And since the energy of light is directly related to its color and wavelength, different elements absorb and emit different colors of light. Consider hydrogen, the simplest atom, with just 1 electron. When you heat hydrogen gas in a flame, the single electron gets excited and jumps to a higher energy level. When it falls back down, it releases light at a very specific wavelength that appears as a particular shade of red. This is called the Balmer series, and it is one of the fingerprints of hydrogen. Other elements produce different colors because their electrons require different amounts of energy to jump between levels. Now, most objects in the world around us are not made of single atoms. They are made of molecules, which are groups of atoms bonded together. In molecules, the situation becomes more complex and more beautiful. When atoms bond together, their electrons do not remain isolated. Instead, they begin to interact, creating new patterns of energy levels. The outermost electrons, called valence electrons, are the ones most involved in bonding and in interactions with light. The structure of a molecule, how many atoms it contains, how they are arranged, what kinds of bonds connect them, determines which wavelengths of light that molecule will absorb. A molecule with a particular structure might absorb blue light very efficiently, while allowing red light to pass through or bounce off. Another molecule with a slightly different structure might absorb red light while allowing green light to pass. This is why changing the structure of a molecule can completely change its color. Consider the family of compounds called azo dyes. By tweaking the chemical structure of these molecules, adding different groups of atoms, changing the positions of bonds, altering the overall geometry, chemists can create versions that appear red, yellow, orange, or many other colors. The same basic molecular skeleton produces entirely different colors depending on how it is constructed. The color is not inherent to the material. It is a consequence of the structure. The electrons in these molecules do not exist in simple shells like they do in isolated atoms. Instead, they occupy molecular orbitals that extend across the entire molecule. Some of these orbitals have lower energy and some have higher energy. The difference in energy between the lowest occupied orbital and the lowest unoccupied orbital determines what color of light the molecule will absorb most efficiently. This energy difference is called the HOMO-LUMO gap, where HOMO stands for highest occupied molecular orbital and LUMO stands for lowest unoccupied molecular orbital. When a photon of light strikes the molecule, if that photon carries exactly the right amount of energy, matching the HOMO-LUMO gap, then the electron can absorb it and jump from the occupied orbital to the unoccupied orbital. If the photon's energy is too small or too large, the electron ignores it and the photon passes through or bounces off. This is why molecules appear transparent to certain colors and absorb other colors. The molecular structure determines which colors are absorbed and which are not. The beauty of this system lies in its precision. The laws of quantum mechanics that govern electron behavior are absolute and deterministic. Given a particular molecular structure, we can predict with remarkable accuracy which wavelengths of light it will absorb. This is why chemists can design new materials with specific colors, why the colors of dyes and pigments are so consistent and reliable, and why the colors of nature follow predictable patterns. As you rest and allow these concepts to settle into your mind, understand that you are learning the language in which atoms speak to light. Every colored object around you is a manifestation of electron behavior, of quantum mechanics expressing itself in the visible world. The electrons are dancing in their shells, absorbing and releasing energy, creating the visual reality that you perceive. In the next moments, we will explore this dance in more detail, discovering how the interaction between light and electrons creates the specific colors that paint our world. When light whispers to atoms, absorption and reflection. Light itself is a wave, a ripple of electromagnetic energy traveling through space at the fastest speed known to exist. It is also a particle, a photon carrying a discrete packet of energy. This dual nature, sometimes acting as a wave, sometimes as a particle, is one of the great mysteries and beauties of quantum mechanics. For understanding color, it is the particle nature of light that matters most. Each photon carries energy proportional to its frequency. High-frequency light, like violet or ultraviolet light, carries more energy per photon. Low-frequency light, like red or infrared light, carries less energy. This relationship between frequency and energy is absolute and unchanging. It is written into the fundamental structure of the universe. When a photon of red light strikes an atom, it carries a specific amount of energy. When a photon of blue light strikes the same atom, it carries more energy. The atom responds differently to each because atoms are selective about the energy they can absorb. When a photon approaches an atom or molecule, something quite remarkable can happen. If the photon's energy exactly matches the energy difference between two electron energy levels in that atom or molecule, the photon can be absorbed. The photon vanishes, transferring all of its energy to the electron. The electron, receiving this energy boost, jumps from its lower energy level to a higher one. The atom is now in an excited state, unstable and eager to return to its ground state. This excited state does not last long. Within fractions of a second, sometimes within picoseconds, the electron falls back down to its original level. When it does, it releases that energy in the form of light. In most cases, it releases the same color of light that was originally absorbed. This is called fluorescence or phosphorescence, depending on the mechanism of the transition. This is why certain minerals glow under ultraviolet light, why highlighter markers appear to glow, and why certain substances seem to emit light when they are illuminated with a different color of light. But there is another possibility. When the photon's energy does not exactly match any electron transition in the atom or molecule, the photon is not absorbed. Instead, it passes through the material or bounces off its surface. This is the mechanism of reflection and transparency. If a material does not absorb a particular color of light, that light passes through or bounces off, and that is the color you see. Consider a piece of colored glass. If you look at red glass, it appears red because the material absorbs the other colors of light, the greens and blues and yellows, while allowing red light to pass through. The red light that reaches your eye is the light that the glass did not absorb. The material has electronic transitions that match the energies of green and blue light, so those photons are absorbed. But the electronic transitions do not match the energy of red light, so red light passes through unabsorbed. This principle applies to all objects. A green leaf appears green because it absorbs red and blue light through the action of pigment molecules like chlorophyll, while allowing green light to pass through or bounce off. The red of a rose comes from pigments that absorb green and blue light while reflecting red light back toward your eyes. The blue of the sky comes from a different mechanism altogether, which we will explore later, but the principle is the same. The object's appearance is determined by what it does to the light that strikes it. When light is absorbed by matter, where does that energy go? Sometimes it is re-emitted as light, as in fluorescence. Sometimes it is converted into heat. When you sit in the sun and feel warmth, you are experiencing the conversion of light energy into thermal energy. Dark colors absorb more light across a wide range of wavelengths, so they convert more light into heat. This is why dark clothing feels hotter in the sun than light clothing. White objects reflect most wavelengths of light, so they absorb less light and remain cooler. The interaction between light and matter is not random or chaotic. It follows precise rules determined by quantum mechanics. The energy levels available to electrons in an atom or molecule are fixed. The energy of a photon is determined by its frequency. When these two factors match, absorption occurs. When they do not match, the photon passes through or reflects. There is a poetry in this precision, a kind of cosmic order that underlies all color. In molecules, the situation is slightly more complex because the energy levels are not as widely separated as they are in isolated atoms. Molecules have vibrational and rotational energy levels in addition to electronic energy levels. An electron can jump to a higher electronic level, and within that higher level, the molecule can vibrate or rotate in different ways. This creates a dense forest of possible energy transitions, allowing molecules to absorb light across a range of wavelengths rather than at a single discrete wavelength. This is why pigments and dyes have absorption spectra, graphs showing how much light they absorb at different wavelengths. Instead of absorbing light at a single wavelength like an isolated atom might, a pigment molecule absorbs light across a range of wavelengths, with the strongest absorption at certain preferred wavelengths. The color you see is the result of this absorption spectrum. If a pigment absorbs strongly in the blue and green regions of the spectrum, it appears red, because red is the color that is not absorbed and therefore reaches your eyes. As we explore further, understand that every color you see is a message from matter about its electronic structure. When you see a colored object, you are literally seeing the consequences of electron behavior. The electrons in the object's atoms and molecules are selectively absorbing certain colors of light and allowing others to pass or reflect. This selective absorption is not a property of the color itself. It is a property of the matter, determined by the arrangement of electrons within its atoms and molecules. The interaction between light and matter is gentle but powerful. A single photon carries an incredibly small amount of energy, yet billions of these photons striking your eye every second create the rich visual experience of the world around you. And in each interaction between a photon and an electron, the laws of quantum mechanics are being obeyed, the fundamental rules of reality are being expressed, and the chemistry of color is being written. The spectrum within, breaking down visible light. Light is a wave, and like all waves, it can be characterized by its wavelength, the distance between successive peaks of the wave. The visible spectrum, the The range of wavelengths that human eyes can detect spans from about 380 nanometers to about 700 nanometers. A nanometer is 1/1000th of a meter, a scale so small that individual atoms are measured in nanometers. The visible spectrum is a narrow slice of the much broader electromagnetic spectrum, which includes radio waves, microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. At the short wavelength end of the visible spectrum sits violet light, with wavelengths around 380 to 420 nanometers. Violet light carries the most energy of any visible light because it has the highest frequency. Photons of violet light are energetic and can excite electrons to higher energy levels than lower frequency light can. At the long wavelength end sits red light, with wavelengths around 620 to 750 nanometers. Red light carries less energy per photon because it has a lower frequency. Between these extremes lies the full rainbow: indigo, blue, green, yellow, and orange. The relationship between wavelength and frequency is inverse. Shorter wavelengths correspond to higher frequencies, and longer wavelengths correspond to lower frequencies. The energy of a photon is directly proportional to its frequency, which means it is also inversely proportional to its wavelength. This mathematical relationship is absolute and unchanging. A photon of blue light always carries more energy than a photon of red light. This is not a matter of opinion or perspective. It is a fact written into the nature of light itself. When white light passes through a prism or a raindrop, it is separated into its component colors. This happens because light is refracted, or bent, as it passes from one medium to another. The amount of refraction depends on the wavelength of the light. Red light, with its longer wavelength, is refracted less than violet light with its shorter wavelength. As a result, the different colors are bent by different amounts and they separate into a rainbow. This separation reveals something profound. White light is not a single color. It is a mixture of all colors, all wavelengths of the visible spectrum combined together. When all these wavelengths strike your eye simultaneously, your brain interprets the combination as white. But if you remove certain wavelengths, the remaining light appears colored. Remove all the red and you see cyan. Remove all the blue and you see yellow. Remove all the green and you see magenta. The colors of objects arise from selective removal of wavelengths from white light. A red object absorbs the other colors and reflects red. A blue object absorbs the other colors and reflects blue. This selective absorption and reflection is the mechanism by which matter creates color. Different materials have different absorption spectra because their electrons have different energy levels, different configurations, different possibilities for transitions. Interestingly, the human eye is not equally sensitive to all wavelengths of visible light. The eye is most sensitive to green light, around 555 nanometers in wavelength, in bright daylight conditions. This sensitivity is not random. It is an evolutionary adaptation. The sun's peak emission is in the green part of the spectrum, so it makes sense that human eyes evolved to be most sensitive to the wavelengths that are most abundant in natural sunlight. This is why green appears so bright and vivid to us, and why red and violet appear somewhat dimmer even at the same intensity. The structure of light as a wave with specific wavelengths is intimately connected to the structure of matter with specific energy levels. An electron in an atom can only exist in certain energy states, separated by discrete energy gaps. A photon of light can only be absorbed if its energy exactly matches one of these gaps. This matching between the wavelength of light and the structure of matter is what creates color. Consider the visible spectrum as a musical scale. Just as a musical scale has specific notes separated by specific intervals, the visible spectrum has specific wavelengths separated by specific frequency intervals. And just as different instruments respond to different notes, a piano can play all notes, a flute can play a certain range, a trumpet can play another range, different materials respond to different wavelengths of light. Some materials absorb a broad range of wavelengths appearing dark, others absorb a narrow range, appearing colored. Some absorb very little, appearing transparent or white. The journey from red to violet across the visible spectrum is not just a change in color. It is a change in energy, in the power carried by each photon, in the ability to excite electrons to higher levels. Red light, gentle and low energy, can only excite electrons that have relatively small energy gaps. Violet light, energetic and high frequency, can excite electrons across much larger energy gaps. This is why ultraviolet light, beyond the violet end of the visible spectrum, is so energetic that it can damage living cells and cause sunburns. The energy is simply too great for biological molecules to handle. As you contemplate the spectrum within light, imagine yourself standing in the light of a sunset. That golden light you see is red and yellow light reaching your eyes, while the blue and violet light has been scattered by the atmosphere. Or imagine a prism in a window, casting a rainbow on your wall. That rainbow is white light separated into its component wavelengths, each wavelength corresponding to a specific energy, a specific frequency, a specific color. And in that rainbow, you are seeing the entire visible spectrum laid out before you, from the lowest energies that human eyes can perceive to the highest. The spectrum is continuous, a smooth gradation from red to violet, yet we divide it into distinct colors: red, orange, yellow, green, blue, indigo, violet. These are not categories that exist in nature. They are categories that exist in human perception and language. In reality, there is no clear boundary between red and orange, or between orange and yellow. The spectrum blends smoothly from one wavelength to the next. But human brains have evolved to categorize this continuous spectrum into discrete color terms, making it easier to communicate and remember colors. Understanding the spectrum within light is understanding the foundation of color. It is recognizing that color is not a property of objects, but a property of light. It is understanding that different wavelengths carry different amounts of energy and have different effects on matter. It is seeing that the visible spectrum, this narrow slice of electromagnetic radiation, is the window through which we perceive the world. Everything we see is filtered through this window, shaped by the wavelengths that our eyes can detect and our brains can interpret. Leaves in transition, the chemistry of autumn colors. Autumn is perhaps nature's most spectacular display of color chemistry. As the days grow shorter and temperatures drop, the leaves of deciduous trees transform from green to gold, orange, red, and purple. This transformation is not arbitrary or magical. It is the result of precise chemical changes within the leaf, a carefully orchestrated sequence of molecular events that has been honed by millions of years of evolution. Throughout spring and summer, leaves are green. This green color comes from chlorophyll, a pigment molecule that is absolutely essential for photosynthesis. Chlorophyll absorbs light, particularly in the blue and red regions of the spectrum, and uses the energy from that light to drive chemical reactions that convert carbon dioxide and water into glucose and oxygen. The green color we see is the light that chlorophyll does not absorb, the light it reflects back into the world. Chlorophyll molecules are complex structures with a central magnesium atom surrounded by a ring of carbon atoms and various side chains. The precise arrangement of electrons in this molecule creates energy levels that correspond to the blue and red regions of the visible spectrum. When a photon of blue or red light strikes the chlorophyll molecule, the photon's energy matches the energy gap between electron levels in the molecule, and the electron absorbs the photon and jumps to a higher level. This excited electron then participates in the chemical reactions of photosynthesis. But chlorophyll is not stable indefinitely. It is constantly being broken down and rebuilt, a process that requires energy and nutrients. In summer, the plant has abundant sunlight and an adequate supply of nitrogen and other nutrients from the soil, so it continuously rebuilds its chlorophyll as it breaks down. The leaf remains green because there is always plenty of chlorophyll present. As autumn approaches, the days grow shorter and the temperatures drop. The plant senses these changes and begins to prepare for winter. It starts to withdraw nutrients from the leaves, pulling nitrogen and other valuable minerals back into the trunk and roots, where they will be stored through the winter. As chlorophyll breaks down and is not replaced, the green color fades from the leaves. But here is where the chemistry becomes beautiful. Chlorophyll is not the only pigment in the leaf. There are other pigments that have been present all along, hidden beneath the dominant green of the chlorophyll. As chlorophyll fades, these other pigments become visible, and the leaf displays colors that were always there, but were masked by the green. The most abundant of these hidden pigments are the carotenoids, molecules that absorb light in the blue region of the spectrum and reflect yellow and orange light. Carotenoids are actually essential for protecting the plant during photosynthesis. They absorb excess light energy that the chlorophyll cannot handle, preventing the formation of harmful free radicals that could damage the leaf cells. Throughout the summer, carotenoids are present in the leaf, working alongside chlorophyll to enable photosynthesis. But their yellow and orange colors are completely obscured by the dominant green of the chlorophyll. As chlorophyll breaks down in autumn, the carotenoids suddenly become visible. The leaf that was green in September becomes yellow or orange in October. The chemistry has not changed. The carotenoids are the same molecules they have always been. But the visual appearance has transformed because the dominant pigment that was masking them has faded away. In some trees, the autumn colors go beyond yellow and orange. Bright reds and purples appear in the leaves, and these come from yet another class of pigments called anthocyanins. Anthocyanins are different from chlorophyll and carotenoids. They are not present in significant amounts during the growing season. Instead, they are synthesized in autumn, produced by the plant specifically as the leaves prepare to fall. The synthesis of anthocyanins requires energy, so the plant only makes them if it is warm enough and sunny enough to make the energy investment worthwhile. The reason anthocyanins are produced in autumn is still not entirely understood, but there are several theories. One theory suggests that anthocyanins help protect the leaves from damage caused by intense sunlight, as the plant is withdrawing nutrients from them. Another theory suggests that the red color serves as a warning to insects that the leaf is unhealthy and not worth laying eggs on. Yet another theory proposes that anthocyanins help the plant reabsorb nutrients from the leaves before they fall. Whatever the function, the chemistry is clear. Anthocyanins are pigment molecules that absorb light in the green and yellow regions of the spectrum, reflecting red and purple light. The molecular structure of anthocyanins is similar to the structure of flavonoids, a large family of pigments found throughout the plant kingdom. The color of anthocyanins can vary depending on the pH of the leaf cells and the presence of other molecules that modify their structure. In acidic conditions, anthocyanins appear more red. In neutral or slightly alkaline conditions, they appear more purple or blue. The autumn transformation of leaves is a stunning example of how chemistry creates color. The pigments that create the colors are always present or are synthesized in response to seasonal signals. The colors emerge not because new molecules appear, but because the balance of pigments changes. The green chlorophyll that dominated the summer colors fades, revealing the yellows and oranges of carotenoids. The plant synthesizes red and purple anthocyanins in response to shortening days and cooling temperatures. The result is a spectrum of colors that seems almost impossible in its beauty. As you contemplate autumn leaves, understand that you are witnessing chemistry in action. Each color tells a story about what is happening inside the leaf. The green of summer speaks of active photosynthesis and the presence of chlorophyll. The yellow and orange of autumn speak of chlorophyll fading and carotenoids becoming visible. The red and purple speak of the plant's response to seasonal changes, the synthesis of protective pigments, as the leaf prepares to separate from the tree. The timing and intensity of autumn colors depends on weather conditions. A warm, sunny autumn with cool nights produces the most vibrant colors because it allows the plant to synthesize anthocyanins and to withdraw nutrients from the leaves efficiently. A cloudy, warm autumn produces duller colors because the plant does not synthesize as many anthocyanins. A sudden hard freeze can lock the colors in place, preserving them for a few weeks before the leaves fall. This transformation happens because the tree is preparing for winter, a time when the soil is frozen and water is unavailable to the roots. By withdrawing nutrients from the leaves before they fall, the tree conserves resources. By shedding its leaves, the tree reduces water loss through transpiration. The colors are a side effect of this physiological process, a beautiful byproduct of the chemistry of seasonal survival. Yet in that byproduct lies one of nature's most magnificent displays of color, a testament to the power of chemistry to create beauty. Minerals and ancient light, gemstones and their hidden colors. Deep within the earth, under tremendous pressure and temperature, minerals grow in silence and darkness. Some of these minerals are gemstones, materials so beautiful that humans have valued them for thousands of years. A ruby glows with deep red light. An emerald displays a rich green. A sapphire shows a brilliant blue. These colors are not painted on the surface. They are intrinsic to the mineral structure, born from the chemistry of the atoms that compose it and the history of geological processes that shaped it. At their heart, most gemstones are simple compounds. Ruby is aluminum oxide, the same chemical compound as the colorless mineral corundum. Emerald is beryllium aluminum silicate, a more complex compound. Sapphire is also aluminum oxide, chemically identical to ruby. Yet rubies are red, sapphires are blue, and they are vastly more valuable than colorless corundum. The difference lies not in the major chemical composition, but in tiny amounts of impurities, trace elements that are incorporated into the crystal structure during formation. Ruby gets its red color from chromium ions, atoms of chromium that have lost electrons and are incorporated into the crystal lattice of aluminum oxide. These chromium ions have a specific electronic structure that causes them to absorb green light strongly, while allowing red light to pass through or reflect. When white light enters a ruby, the chromium ions absorb the green and allow the red to emerge. The intensity and purity of the red color depends on how much chromium is present. Too little chromium, and the stone appears pale. Too much, and the stone appears almost black. The chromium ions in a ruby are not randomly distributed. They occupy specific positions in the crystal lattice, replacing some of the aluminum ions. The crystal lattice itself is a regular, repeating three-dimensional pattern of atoms held together by electromagnetic forces. This regular pattern is crucial to the gemstone's properties. If the atoms were randomly arranged, as they are in glass or an amorphous solid, the stone would be cloudy and would not have the same optical properties. The process of forming a ruby is slow and patient. It requires the right temperature, the right pressure, and the presence of chromium. In nature, rubies form in metamorphic rocks, rocks that have been transformed by intense heat and pressure deep within the earth. As these rocks are subjected to the extreme conditions of the Earth's interior, the atoms rearrange themselves into new structures. If chromium is present in the right amount, rubies form. This process can take millions of years. Sapphires, though chemically identical to rubies, get their blue color from different impurities. Iron and titanium ions in the crystal lattice create energy levels that correspond to yellow and red light. When white light enters a sapphire, these impurities absorb the yellow and red, allowing the blue to emerge. Again, the intensity of the color depends on the concentration of the impurities. The exact shade of blue depends on the ratio of iron to titanium. Emeralds are more complex. They are beryllium aluminum silicates, and their green color comes from chromium ions, the same impurity that makes rubies red. Yet in an emerald, chromium creates green rather than red. This difference arises from the different crystal structure of the emerald. The chromium ions are in a different chemical environment, surrounded by different atoms, and this different environment shifts the energy levels. The same impurity creates different colors in different minerals because the crystal structure determines what happens to the light. This principle extends to all colored gemstones. The color is determined by the interplay between the crystal structure and the impurities present. Diamonds are pure carbon, colorless if pure, but can be colored yellow by nitrogen, blue by boron, pink by defects in the crystal structure, or brown by structural damage. Topaz can be colorless, yellow, blue, pink, or brown depending on trace elements and irradiation by natural radiation in the earth. One of the most fascinating aspects of gemstone color is the phenomenon of pleochroism, where a single crystal appears different colors when viewed from different directions. This happens because the crystal structure is not the same in all directions. The electrons in the crystal respond differently to light coming from different directions, absorbing different wavelengths depending on the direction of the light. A pleochroic crystal might appear red when viewed from one direction and orange when viewed from another. Gemstone cutters use knowledge of pleochroism to orient stones so that the most beautiful color is visible from the viewing angle. Some gemstones exhibit another phenomenon called fluorescence. When exposed to ultraviolet light, they emit visible light. A ruby that appears red in ordinary light might glow a deeper red under ultraviolet light. This happens because the ultraviolet light excites electrons to very high energy levels, and when they fall back down, they release energy in the form of visible light. Different gemstones fluoresce different colors under ultraviolet light, and this property can be used to identify them. The colors of gemstones are records of geological history. The presence of chromium tells us that the rock containing the ruby or emerald formed in an environment where chromium was available. The color's intensity tells us about the conditions of formation. The crystal structure tells us about the temperature and pressure that existed during formation. In a sense, each gemstone is a time capsule, preserving information about the Earth's interior millions of years ago. As you contemplate a colored gemstone, understand that you are looking at ancient light. The photons that are being absorbed and reflected by the impurities in the stone are interacting with atoms that have been in place for millions of years. The colors you see are the result of a deep geological process, a transformation of matter under extreme conditions, and the incorporation of trace elements that were present in the right place at the right time. The mining and cutting of gemstones is an art form based on understanding this chemistry. Miners search for rocks that contain the right impurities in the right concentrations. Cutters orient the stones to display their best colors. Jewelers set them in precious metals to enhance their beauty. All of this is possible because we understand the chemistry of color in gemstones, because we know how atoms and light interact to create these beautiful materials. Wings of illusion, structural color in nature. Not all color in nature comes from pigments. Some of the most spectacular colors in the living world are created not by molecules that absorb and reflect certain wavelengths, but by the physical structure of the material itself. A butterfly's wing does not necessarily contain blue pigment, yet it appears brilliantly blue. A peacock's tail feather shimmers with colors that seem to change as you move. A hummingbird's throat glows with iridescent colors that appear and disappear. These colors are created by the interaction of light with the physical structure of the material, a phenomenon called structural color. Structural color arises from the way light interacts with tiny structures that are smaller than the wavelength of visible light. On a butterfly's wing, the surface is covered with thousands of tiny scales, each one only a few micrometers in size. These scales are not smooth. They have ridges and grooves, layers of material arranged in precise patterns. When light hits these structures, it reflects off multiple surfaces, creating patterns of constructive and destructive interference. Constructive interference occurs when light waves that have reflected off different surfaces travel the same distance before reaching your eye. These waves are in phase, meaning their peaks and troughs align. When in-phase waves combine, they reinforce each other, creating a brighter reflection. Destructive interference occurs when the light waves that have reflected off different surfaces have traveled different distances, putting them out of phase. When out-of-phase waves combine, they cancel each other out, creating darkness. The color produced by structural color depends on the spacing of the structures. If the ridges and grooves on a butterfly's wing are spaced so that blue light undergoes constructive interference, then blue light is reflected brightly. Red light, with its longer wavelength, might not fit the spacing properly and might undergo destructive interference, so red light is absorbed or scattered. The result is that the wing appears blue, not because of blue pigment, but because of the physical structure. The remarkable thing about structural color is that it can change depending on the angle of viewing. The spacing of the structures is fixed, but the path length of the light changes as you move your viewing angle. At one angle, blue light might undergo constructive interference. At a different angle, green light might undergo constructive interference. This is why iridescent colors shift and change as you move. The color is not a property of the light or the pigment. It is a property of the geometry of the situation. This principle is used by nature in countless ways. Peacocks use it to create the spectacular tail displays that are crucial to their mating behavior. The feathers contain no blue pigment, yet they appear brilliantly blue because of the layered structure of the keratin protein in the feather. Hummingbirds use structural color in their gorgets, the iridescent throat patches that attract mates and are used in territorial displays. The color changes dramatically as the bird moves, sometimes appearing almost black, sometimes flashing brilliant red or green. Many beetles and insects use structural color. The elytra, the hardened wing covers of beetles, often display iridescent colors created by multi-layered structures. Some beetles appear to glow with metallic green or copper colors that seem almost artificial in their intensity. Yet these colors are entirely natural, created by the interaction of light with the chitinous structure of the exoskeleton. The advantage of structural color over pigmentary color is that it can be more intense and more efficient. A pigment must absorb light, converting it to heat, or using it in chemical reactions. This always involves some energy loss. But structural color reflects light through interference, using the wavelength selective properties of the structure itself. Very little light is lost. The color can be incredibly bright and vivid. Structural color is also more stable than pigmentary color. A pigment molecule can be degraded by light, heat, or chemical attack, but a physical structure, made of protein or chitin or other biological materials, can persist for the lifetime of the organism. This is why the brilliant colors of butterflies and beetles can last indefinitely as long as the structure remains intact. The physics of structural color is the same as the physics of thin film interference, the phenomenon that creates the colors of soap bubbles or oil films on water. When light reflects off the top surface of a thin layer and also reflects off the bottom surface, the two reflected rays can interfere with each other. Depending on the thickness of the layer and the wavelength of the light, the interference can be constructive or destructive. This is why a soap bubble appears different colors at different spots, and why the colors change as the bubble gets thinner and eventually pops. Nature has evolved this structural color in countless organisms. Some scientists believe that the original function of these structures was not color, but structural integrity. The layered, ribbed structures provide strength and rigidity. The color effect might have been an accidental byproduct that was then selected for because it was useful for communication, camouflage, or mating displays. Over millions of years, evolution has refined these structures to create the spectacular colors we see today. Humans have recently begun to mimic structural color in artificial materials. Researchers have created synthetic structures that produce iridescent colors without pigments. These materials could be used for displays, paints, fabrics, and other applications where color is important. The advantage is that structural colors do not fade like pigments do. They do not require dyes that might be toxic or environmentally problematic. They are purely physical, based on geometry rather than chemistry. As you contemplate a butterfly wing or a peacock feather, understand that you are witnessing light interacting with physical structure. The colors are real, but they are not the result of molecules absorbing and reflecting light. They are the result of tiny structures, invisible to the naked eye, arranged in precise patterns that cause light waves to interfere constructively and destructively. In that interference, color is born, not from pigment, but from geometry, not from absorption, but from reflection and the wave nature of light. The ocean's blue mystery, water and color absorption. If you have ever looked at the ocean on a clear day, you have been struck by its blue color. The blue of the ocean seems profound, almost infinite, stretching toward the horizon and inviting you to contemplate the vastness of the world. Yet water itself, when you hold it in a glass, appears colorless. A single glass of water is transparent. How can a substance that appears colorless when you look at a small amount appear intensely blue when you look at a vast quantity? The answer lies in selective absorption. Water absorbs light, but it does not absorb all wavelengths equally. Water molecules are relatively transparent to red light. A photon of red light can travel through water without being absorbed, bouncing from water molecule to water molecule, but eventually passing through. But water absorbs blue light much more efficiently. A photon of blue light striking a water molecule is much more likely to be absorbed. Its energy transferred to the water molecule. This selective absorption is a consequence of the molecular structure of water. A water molecule consists of two hydrogen atoms bonded to an oxygen atom in a bent configuration. The electrons in these bonds have energy levels that correspond to the infrared region of the spectrum. However, water is not perfectly transparent to visible light. There is some absorption across the entire visible spectrum, but the absorption is not uniform. The absorption spectrum of water shows that red light, with its longer wavelength and lower energy, is absorbed relatively weakly. As you move towards shorter wavelengths and higher energies, the absorption increases gradually. By the time you reach blue light, the absorption is significantly stronger. The absorption continues to increase as you move toward ultraviolet light. This wavelength-dependent absorption is why the ocean appears blue. When white light enters the ocean, the red components are absorbed more readily than the blue components. As the light penetrates deeper into the water, more and more of the red light is absorbed. The light that is reflected back toward the surface is depleted in red wavelengths and enriched in blue wavelengths. This reflected light, reaching your eyes, appears blue. The intensity of the blue color depends on the depth of the water and the clarity of the water. In a shallow, clear ocean, the blue is lighter, almost cyan, because the light does not have to travel as far through the water before being reflected back. In a deep ocean, especially if the water is very clear, the blue is darker and more intense because the light has traveled farther, more red has been absorbed, and the reflected light is strongly depleted in red wavelengths. In turbid water, water that contains suspended particles of sediment or plankton, the color is different. These particles scatter light, reflecting it back before it has traveled far into the water. The scattered light still contains red wavelengths, so turbid water appears greenish or brownish rather than blue. This is why rivers often appear brown or green, even though they contain water that is intrinsically colorless. The color comes from suspended sediment and organic matter, not from the water itself. The selective absorption of water is not uniform across the blue region of the spectrum. Water absorbs different shades of blue with different efficiencies. This is why the ocean in different parts of the world can appear different shades of blue. In some regions, the water is a lighter cyan blue. In others, it is a deeper, darker blue. The difference depends on the specific absorption spectrum of water at those wavelengths and the depth and clarity of the water. At depths below about 100 meters, where even blue light has been largely absorbed, the ocean appears black. The little light that penetrates to these depths is so depleted that it appears almost completely dark. Yet even in this darkness, light is still present. Organisms that live in the deep ocean have evolved to see in this dim blue light, and some have evolved to produce their own light through bioluminescence. The blue color of the ocean is also affected by the sky. On an overcast day, the ocean appears gray because the scattered light from the clouds is being reflected by the water surface and mixed with the light that has been scattered by the water itself. On a clear day with a blue sky, the ocean appears a deeper blue because the sky is contributing blue light to the water surface, and this blue light is being reflected and mixed with the light that has been scattered by the water itself. This interplay between water's intrinsic color and the reflected light from the sky has fascinated humans for millennia. Poets have written about the blue of the ocean, artists have painted it, and philosophers have contemplated it. Yet the explanation is straightforward. Water absorbs red light more readily than blue light, and the blue light that is reflected or scattered back toward the surface creates the color we perceive. The ocean is not uniformly blue. Different regions have different colors depending on the presence of phytoplankton, the microscopic plants that form the base of the marine food chain. When phytoplankton bloom, they turn the water green or brown because they contain chlorophyll and other pigments. The satellite images of phytoplankton blooms show swirls of green and brown in the blue ocean, creating patterns of extraordinary beauty. These colors are not coming from the water or from the sky. They are coming from the billions of tiny organisms suspended in the water, organisms that are themselves colored by the chemistry of pigment molecules. As you think about the ocean's blue color, you are thinking about the interaction of light with matter on a vast scale. The absorption spectrum of water, a property determined by the electronic structure of water molecules, creates the blue color that defines our perception of the ocean. The ocean's blue is a reminder that color is not an intrinsic property of objects. It is a consequence of how light interacts with matter, how photons interact with electrons, how the quantum world reveals itself through the colors we see. Rust and fire, the chemistry of warm colors. Red and orange are the colors of fire, of heat, of energy being released. They are warm colors, colors that seem to radiate heat even when they are not actually warm. In nature, these warm colors often arise from oxidation, the process by which atoms lose electrons and combine with oxygen. The most familiar example is rust, the red-brown coating that forms on iron when it is exposed to oxygen and water. When iron is exposed to air and moisture, the iron atoms at the surface begin to lose electrons to oxygen molecules. This process is oxidation, and it is a chemical reaction that releases energy. The product is iron oxide, a compound in which iron atoms have bonded with oxygen atoms. There are several different iron oxides, and they have different colors. Iron oxide with 2 oxygen atoms per iron atom, called ferrous oxide or wistite, is black. Iron oxide with 3 oxygen atoms per iron atom, called ferric oxide or hematite, is red. A mixture of ferrous and ferric oxide, called magnetite, is black. The rust that forms on iron objects exposed to rain or moisture is typically a mixture of ferrous and ferric oxides, which gives it a reddish-brown color. The exact color depends on the ratio of ferrous to ferric oxide and on the degree of hydration. How much water is incorporated into the crystal structure. Fully hydrated rust can be orange or yellow. Partially hydrated rust is reddish-brown. Dehydrated rust is darker red or brown. The red color of iron oxide arises from the electronic structure of the ferric ion. When iron loses 3 electrons, the remaining electrons are arranged in a configuration that absorbs light in the green region of the spectrum. The light that is not absorbed, the red light, is reflected back, creating the red color we perceive. The absorption spectrum of ferric iron is well understood, and the color can be predicted from the electronic structure of the ion. On Mars, the surface is colored red and orange because it is covered with iron oxide dust. The Martian soil contains a high concentration of ferric iron oxides, the same compounds that create rust on Earth. The Martian atmosphere is thin and offers little protection from solar radiation. So the iron in the Martian rocks has been oxidized by the oxygen that is released when ultraviolet light breaks apart carbon dioxide molecules in the atmosphere. Over billions of years, this process has created the rusty red surface that we see in images from Mars rovers. Another warm color in nature comes from copper and its compounds. When copper is exposed to oxygen, it oxidizes to form copper oxide, which is black. But when copper is exposed to water and carbon dioxide, it forms a compound called copper carbonate, which is blue-green or green. This is the patina that forms on old copper roofs and copper statues. The Statue of Liberty appears green because the copper exterior has oxidized to form this green patina over more than 100 years of exposure to the elements. The green of the patina is distinct from the warm colors of iron oxide, but both arise from oxidation processes. The green of copper carbonate comes from the electronic structure of the copper ion and the carbonate ion. The absorption spectrum of copper carbonate is such that green light is reflected, while red light is absorbed, creating the blue-green color. Fire itself produces warm colors through a different mechanism. When a substance burns, the heat breaks chemical bonds and excites atoms to high energy levels. As these atoms fall back to lower energy levels, they emit light. The color of the flame depends on what atoms are burning. Hydrogen burns with a nearly invisible blue flame because the excited hydrogen atoms emit light in the ultraviolet region. Sodium burns with a bright yellow flame because the excited sodium atoms emit light at a specific wavelength in the yellow region. Copper compounds burn with a green or blue flame because the excited copper atoms emit light in those regions. Fireworks use this principle to create displays of colored light. Different metal compounds are added to the firework mixture to produce different colors. Strontium compounds produce red, barium compounds produce green, copper compounds produce blue, sodium compounds produce yellow. The heat of the explosion excites the atoms in these compounds, and as they fall back to lower energy levels, they emit light of characteristic colors. The display of colors in a fireworks show is a display of atomic spectroscopy, the phenomenon of atoms emitting light at characteristic wavelengths. The warm colors of fire and rust and oxidation are reminders that color often arises from chemical change. When atoms rearrange themselves into new configurations, When electrons are transferred from one atom to another, when new bonds are formed, the electronic structure changes. And when the electronic structure changes, the colors change. The red of rust is the color of iron atoms that have lost electrons to oxygen. The yellow of a sodium flame is the color of sodium atoms that have been excited by heat and are falling back to lower energy levels. As you contemplate a rusty object or a sunset painted in warm colors, understand that you are witnessing chemistry in action. The warm colors are not arbitrary or accidental. They are consequences of the electronic structure of the atoms and molecules involved. Consequences of the laws of quantum mechanics that govern how electrons behave. The universe has written its chemistry in colors, and those colors tell the story of what is happening at the atomic level. The warm colors of autumn leaves, the red of a sunset, the orange of fire, the green patina of old copper. All of these arise from the interaction of light with the electronic structure of matter. Understanding the chemistry of warm colors is understanding how nature paints with atoms and light, how the microscopic world of electrons creates the visible colors that surround us and make our world beautiful. Bioluminescence. Living light without heat. In the deep ocean, far below the reach of sunlight, there is light. Creatures drifting through the darkness emit their own light, creating tiny stars in the abyss. This is bioluminescence, the production of light by living organisms through chemical reactions. It is one of the most magical phenomena in nature, a reminder that light can be created not by heat or electricity, but by the careful orchestration of chemical reactions within living cells. Bioluminescence is not the same as fluorescence. In fluorescence, an organism absorbs light from an external source and re-emits it. In bioluminescence, the organism creates light through a chemical reaction that releases energy in the form of photons. The energy is not provided by heat or electricity, but by the chemical energy released when molecules react with each other. The most well-known bioluminescent organisms are fireflies, beetles that live in warm regions and produce flashing lights during their mating season. A firefly's light comes from a chemical reaction between a compound called luciferin and an enzyme called luciferase, in the presence of oxygen and a high-energy compound called ATP. When these chemicals react, the reaction releases energy that excites electrons to high energy levels. As these electrons fall back to lower levels, they emit photons of light, typically in the yellow-green region of the spectrum. The remarkable thing about firefly bioluminescence is its efficiency. Almost all of the energy released by the chemical reaction is converted into light. Very little is wasted as heat. This is in sharp contrast to an incandescent light bulb, where most of the electrical energy is converted into heat, and only a small fraction is converted into visible light. Fireflies have evolved a chemical system that converts chemical energy directly into light with extraordinary efficiency. The luciferin-luciferase reaction is not unique to fireflies. Similar reactions are found in many organisms. Marine organisms like dinoflagellates, jellyfish, and fish use variations of this reaction to produce light. The specific luciferin and luciferase molecules vary among different species, but the principle is the same. A substrate molecule is oxidized by an enzyme in the presence of oxygen, releasing energy that excites an electron to a high energy level. When the electron falls back down, it emits a photon. The color of bioluminescent light varies among species and is determined by the electronic structure of the molecule that emits the light. Fireflies emit yellow-green light. Some jellyfish emit blue light. Some fish emit red light. The color is not arbitrary. It is determined by the energy gap between the ground state and the excited state of the electron. The larger the energy gap, the higher the frequency of the emitted light, and the shorter the wavelength. In the deep ocean, where bioluminescence is particularly abundant, the colors are typically blue and green. This is not accidental. Blue and green light penetrates water more efficiently than red light. An organism that produces red bioluminescence in the deep ocean would be wasting its energy because the red light would be absorbed quickly and would not travel far. Organisms that produce blue or green light have a much greater chance of their light being seen by other organisms, whether for communication, attraction of mates, or hunting. Some organisms use bioluminescence for defense. When a fish is attacked, it releases a cloud of bioluminescent dinoflagellates. The sudden flash of light startles the predator and allows the fish to escape. Other organisms use bioluminescence to attract prey. An anglerfish dangles a bioluminescent lure in front of its mouth, and smaller fish are attracted to the light, only to be eaten. Still other organisms use bioluminescence for communication, flashing patterns of light to signal to other members of their species. The chemical reactions that produce bioluminescence are controlled by the organism's nervous system. A firefly can produce flashes of light in a specific pattern, a code that is recognized by other fireflies of the same species. Different species have different flashing patterns, and these patterns are crucial for mating. A female firefly recognizes the flashing pattern of a male of her species and responds with her own flashing pattern, allowing the two to find each other in the darkness. The efficiency of bioluminescence has inspired scientists to explore how similar reactions might be used to create new sources of light. Researchers have isolated luciferin and luciferase from fireflies and used them in laboratory experiments. They have even engineered organisms to produce bioluminescent proteins, like the green fluorescent protein that is commonly used as a marker in biological research. These applications show how understanding the chemistry of natural bioluminescence can lead to practical applications. Bioluminescence is a reminder that light is not just something that comes from the sun or from electrical devices. Light is a product of chemistry, a consequence of electrons falling from high energy levels to low energy levels and releasing photons in the process. In every bioluminescent organism, this fundamental principle of quantum mechanics is at work, creating light in the darkness and making the deep ocean glow with life. As you contemplate the idea of creatures creating light through chemistry, understand that you are contemplating one of the deepest mysteries of nature. How did these organisms evolve the ability to produce light? How did natural selection favor the development of complex chemical systems that serve no purpose except to produce light? The answers involve millions of years of evolution, countless small changes that accumulated over time, and the persistence of traits that provided advantages in survival or reproduction. Yet the chemistry itself is not mysterious. It is well understood. We know the molecules involved, the reactions that occur, the energy that is released, and how that energy is converted into photons. Bioluminescence is nature's way of proving that chemistry can create light, that the organization of matter and the flow of electrons can produce the same electromagnetic radiation that travels to us from the sun and the stars. The cosmic palette. Colors across the universe. Beyond Earth, beyond the blue oceans and green forests and rusty deserts, lies a universe painted in colors that tell stories of distant chemistry. The planets of our solar system display a palette of colors, each one revealing something about the composition and conditions of that world. Neptune appears deep blue, a color that speaks of methane in its atmosphere. Jupiter displays bands of orange, brown, and white, colors that arise from complex chemistry in its turbulent clouds. Saturn's pale yellow-white appearance reflects its composition of hydrogen and helium, with traces of other compounds. The blue of Neptune comes from methane in its atmosphere. Methane molecules absorb red light through the same mechanism that we have explored throughout this journey. Electrons absorbing photons, whose energy matches the energy gaps between electron levels. Methane is particularly efficient at absorbing red light, so when white light from the sun enters Neptune's atmosphere, the red light is absorbed and scattered, while the blue light is reflected back toward space. The result is a planet that appears intensely blue, a color that is as much a statement about atmospheric chemistry as it is a visual phenomenon. Jupiter's colors are more complex. The planet has a thick atmosphere composed primarily of hydrogen and helium, but with traces of other compounds. The colors we see are not the colors of hydrogen and helium, which are colorless gases. Instead, they are the colors of compounds formed from other elements that are present in trace amounts. Ammonia ice crystals appear white. Sulfur compounds appear yellow and orange. Complex organic compounds called chromophores appear brown and reddish. The exact composition and colors of Jupiter's atmosphere change over time as the atmosphere circulates and chemical reactions occur. Saturn, though composed of similar materials to Jupiter, appears paler and less colorful. This is because Saturn's atmosphere is colder and more stable. Fewer chemical reactions occur, so fewer colored compounds form. The atmosphere is dominated by white ammonia ice clouds, with only subtle hints of color from trace compounds. Yet even this pale appearance is revealing. It tells us that Saturn is a cold, stable world, and that its atmosphere is dominated by simple, colorless compounds. The other planets in our solar system also reveal their composition through color. Mars appears red because of iron oxide dust on its surface. Venus appears yellowish-white because of sulfuric acid clouds in its atmosphere. Mercury appears gray and cratered because of its ancient airless surface. Each color is a clue about the chemistry and geology of that world. Beyond the planets lie the stars, and the colors of stars reveal their temperatures and compositions. The hottest stars appear blue. Blue light has a shorter wavelength and higher frequency than other visible light, which means it carries more energy per photon. The sun appears yellow because it is moderately hot. The hottest stars in the universe, with surface temperatures of over 30,000 Kelvin, appear blue-white. The coolest stars, with surface temperatures below 4,000 Kelvin, appear red. The relationship between temperature and color is described by Wien's displacement law, which states that the peak wavelength of light emitted by a hot object is inversely proportional to its temperature. A hotter object emits light with a shorter peak wavelength, appearing bluer. A cooler object emits light with a longer peak wavelength, appearing redder. This is why hot coals glow red, and why the filament of an incandescent light bulb appears yellow or white, depending on how hot it is. Stars also reveal their composition through spectroscopy, the analysis of light that has passed through or been emitted by matter. When light from a star passes through its own atmosphere, atoms in the atmosphere absorb specific wavelengths of light, creating dark lines in the spectrum called absorption lines. These lines are like a fingerprint, unique to the elements present in the star's atmosphere. Hydrogen creates one set of lines, helium creates another, iron creates yet another. By analyzing these lines, astronomers can determine what elements are present in a star and in what quantities. The colors we observe in distant galaxies also tell stories about their composition and structure. Spiral galaxies like the Milky Way appear to have a yellow or white bulge in the center, surrounded by blue spiral arms. The yellow bulge is composed of older stars, which are cooler and appear redder. The blue spiral arms are composed of younger, hotter stars. The different colors reflect the ages of the stars in different parts of the galaxy. Nebulae, vast clouds of gas and dust in space, display colors that arise from the gases they contain. Hydrogen nebulae appear red because hydrogen emits light at a specific wavelength in the red region of the spectrum when it is ionized by ultraviolet light from nearby stars. Oxygen nebulae appear green or blue because ionized oxygen emits light at those wavelengths. Sulfur nebulae appear red because ionized sulfur emits light in the red region. The colors of the cosmos are a display of chemistry on the grandest scale. Every color tells a story about temperature, composition, age, or the presence of specific elements. The universe is not a uniform gray. It is painted in colors that span from deep blue to brilliant red, colors that reveal the secrets of distant worlds and the fundamental nature of matter and energy. As you contemplate the colors of the universe, understand that you are looking at the same principles that create color on Earth. The same laws of quantum mechanics that govern the behavior of electrons in atoms on Earth govern the behavior of electrons in distant stars. The same relationships between wavelength, frequency, and energy apply throughout the cosmos. The chemistry of color is universal, written into the fabric of reality itself, expressing itself wherever matter and light interact. The light within you, how your eyes perceive color. We have journeyed from the quantum mechanical behavior of electrons in atoms through the chemistry of pigments and minerals to the colors of distant planets and stars. Now we turn our attention inward to the remarkable organ that allows you to perceive all these colors, your eye. The eye is not a passive receiver of light. It is an active participant in the creation of color, a sophisticated biological instrument that translates light into electrical signals and ultimately into the experience of color that exists in your mind. Light enters the eye through the cornea a transparent dome on the front of the eye that helps focus the light. The light then passes through the pupil, the opening in the iris, and through the lens, which adjusts its shape to focus the light precisely on the retina at the back of the eye. The retina is a thin layer of tissue containing millions of light-sensitive cells called photoreceptors. There are two types of photoreceptors, rods and cones. Rods are sensitive to dim light and allow you to see in low light conditions. They contain a pigment called rhodopsin, which is composed of a protein called opsin bound to a molecule called retinal, which is derived from vitamin A. When a photon of light strikes the rod cell, it is absorbed by the rhodopsin molecule. The photon's energy causes the retinal molecule to change shape, triggering a cascade of chemical reactions that ultimately produces an electrical signal. Rods are not sensitive to color. They respond roughly equally to all wavelengths of visible light. This is why in dim light you cannot see colors. When you are in a dark room and your eyes have adjusted to the darkness, you can see shapes and objects, but they appear in shades of gray. This is because in dim light, your vision relies primarily on rods, which do not distinguish colors. Cones, on the other hand, are responsible for color vision. They are less sensitive to light than rods, so they function primarily in bright light. There are three types of cones, each containing a different pigment that is sensitive to different wavelengths of light. These pigments are called photopsins, and they are similar to rhodopsin, but with slight differences in structure that make them sensitive to different wavelengths. The first type of cone contains a pigment that is most sensitive to short wavelength light in the blue region of the spectrum. These are sometimes called blue cones or S cones, where S stands for short wavelength. The second type contains a pigment that is most sensitive to medium wavelength light in the green region. These are called green cones or M cones. The third type contains a pigment that is most sensitive to long wavelength light in the red region. These are called red cones or L cones. Each type of cone cell responds to a range of wavelengths, not just a single wavelength. Blue cones are most sensitive to blue light, but they also respond to some extent to green and violet light. Green cones are most sensitive to green light, but they also respond to some extent to blue and yellow light. Red cones are most sensitive to red light, but they also respond to some extent to yellow and orange light. The sensitivity curves of the three types of cones overlap, creating a system that can distinguish many different colors. When light of a particular color enters your eye, it stimulates the three types of cones to different degrees. Red light stimulates red cones strongly, green cones moderately, and blue cones weakly. Green light stimulates green cones strongly, red and blue cones moderately. Blue light stimulates blue cones strongly, red and green cones weakly. The pattern of stimulation across the three types of cones is unique for each color, and this pattern is what allows you to distinguish colors. The electrical signals produced by the cone cells are transmitted to the bipolar cells and then to the ganglion cells. The ganglion cells send their signals along the optic nerve to the brain, specifically to the visual cortex at the back of the brain. In the visual cortex, these electrical signals are processed and integrated into the conscious perception of color that you experience. It is important to understand that color is not a property of light or of objects. It is a product of your nervous system's interpretation of the signals from your eyes. Two people looking at the same object might perceive it as slightly different colors if their cone sensitivities are different, or if their brains process the signals differently. Some people are colorblind, meaning that they lack one of the three types of cones. A person who lacks red cones cannot distinguish between red and green, because both colors produce the same pattern of stimulation in their remaining cones. The brain uses the signals from the three types of cones to construct a color space, a mental representation of all possible colors. In this color space, colors that are similar are located near each other, and colors that are very different are located far from each other. The brain also uses other information to determine color, including the brightness of the light, the context of the surrounding colors, and memory and expectation. This is why color perception is not absolute, but relative. A color might appear different depending on what colors surround it. This is called color contrast or simultaneous contrast. A gray square on a white background appears darker than the same grey square on a black background. A color surrounded by its complementary color appears more saturated and vivid. The brain is constantly comparing colors to their context and adjusting the perception to extract the most useful information. The perception of color is also affected by the adaptation of the eye. If you stare at a bright red light for a long time, the red cones become less sensitive to red light. If you then look at a white surface, it will appear cyan because the red cones are less responsive and the blue and green cones dominate. This is called afterimage, and it is a consequence of the cone cells adapting to prolonged stimulation. As you complete this journey through the chemistry of color, understand that color is a collaboration between the external world and your internal perception. The external world provides light and matter that interact according to the laws of quantum mechanics. Your eyes and brain provide the biological machinery that translates these physical phenomena into the conscious experience of color. Neither the external world nor your internal perception alone creates color. Color emerges from the interaction between them. The colors you see right now, the colors that fill your visual world, are the result of billions of years of evolution that has shaped your eyes and brain to perceive light and distinguish colors. They are the result of the laws of physics and chemistry that govern how electrons absorb and emit photons. They are the result of the remarkable ability of your brain to process sensory information and create a rich, detailed model of the visual world. Thank you for joining me on this journey through the invisible world of atoms and electrons, through the chemistry of pigments and minerals, through the colors of nature and the cosmos, and finally into the mechanism of your own perception. If this exploration has brought you a sense of peace and wonder, I would deeply appreciate a like and a subscription to the Relaxing Science channel. Please also share in the comments whether you have discovered new ways of understanding color through this experience, or if there is a particular color in nature that now holds new meaning for you. The chemistry of color is a bridge between science and poetry, between the microscopic world of atoms and the vast cosmos of distant stars. It is a reminder that beauty and understanding are not opposites, but partners. The more we understand about how color is created, the more magnificent the colors of the world become. As you move forward from this moment, carry with you the knowledge that every color you see is a message from the universe, written in the language of electrons and photons, telling the story of how light and matter dance together to create the visual richness of existence. We invite you to return to the Relaxing Science channel for more explorations of the natural world, more journeys into the hidden chemistry and physics that shape our reality. Until then, may you find peace in contemplating the colors around you. May you feel a sense of wonder at the elegance of nature's design, and may you rest well knowing that you are surrounded by the poetry of physics and the art of chemistry, expressed in every color you perceive. End of screenplay total.